ao vivo, Renato.
Ok. Tô dentro?
Uhum.
Okay. All right. Welcome, everybody. Boa tarde to the second talk of our weekly series of colloquium for the National Observatory. This week, it's my pleasure to introduce to you Dr. Eric Fisher. He's a researcher at the University of Michigan in the Department of Climate and Space Science and Engineering. He got his diploma in the Technische Universität in Braunschweig in 2011, his PhD from the University of Michigan in 2018, and working on, well, you correct if I'm wrong, but studies of formation of salt water on Mars.
Pretty much, yes.
All right. So he's part of the science team collaborator on the Mars mission and in the group for the Environmental Dynamics Analyzer MEDA instrument, which is actually at Perseverance right now. He is also and was and is science team collaborator of the Mars Science Laboratory Rover Environmental Monitoring Station called REMS. The instrument went back in, I think, 2012 in Curiosity and still working. So basically have a double job there with these two instruments. Well, he got two awards, achievement awards from the NASA Mars Science Laboratory, one 2015, another one 2017, and has been working very intensely on Mars and Mars atmospheric events, and now perhaps is going to give us insight view of the new Perseverance. So without further ado, I'll pass the word to Eric.
All right, thank you very much for the introduction. I'm just going to go share my screen here. See if this is working. All right, you should be able, hopefully, to see my first slide here.
Yeah.
Perfect.
All right. Well, hello, everyone. Thank you very much for the nice introduction. I am Eric Fisher from the University of Michigan, and it is really my pleasure to be here with you today. I want to thank the National Observatory for the invitation and also Renato for organizing this and inviting me. Today, I'll give you an overview of the Mars 2020 mission, which, as you've probably heard, has been operating on Mars successfully now for, I think, today, 55 sols or Martian days. And so I'll start with a broad overview, and towards the end of my presentation, I'll go a little more into detail about my personal specific involvement with the mission and my scientific interest in it. About myself, I'm a participating scientist on this mission, and in particular, I worked on the calibration of one of the instruments on board that I'll describe a little later, and I also regularly work on surface operations. Please, if this works through this medium here, feel free to interrupt me. Otherwise, you can also feel free, we can have some question session in the end if you have any questions. All right. So that was already pretty much covered here, all about myself. I'm currently a postdoctoral researcher here at the University of Michigan, where I also got my PhD in the past. You might hear it on my accent. I'm from Germany originally, and that's where I started my studies in aerospace engineering. So why do we actually go to Mars, and how easy is it to send a mission to Mars? This here shows our entire Mars exploration family portrait. The text might be a little small, so this is not important. It's just to show you that there have been a lot of attempts to get to Mars. In total, about close to 50 missions have been sent to Mars from 8 different countries or institutions, from the Soviet Union, the United States, Russia, Japan, the European Space Agency.
Eric, I'm sorry to interrupt. There is some kind of echo.
Soviet Union, United States, Russia, Japan, European Space Agency.
Eric, I'm sorry to interrupt. There is some kind of echo. Simone, do you know what's happening? Simone, do you know what's happening?
I just muted myself for 10 seconds there. So was that the problem?
I don't know, there was a problem, but I think it's solved now.
There is a little echo of what he's saying. It's being.
I don't know, there was a problem, but I think it's solved now.
There is a little echo of what he's saying. It's being.
I don't know, there was a problem, but I think it's solved now. I don't know. Renata, are you following in the Renata, are you following? Renato? Okay, I think we have some problem. Let me see how to.
Yeah, I'm not sure if it's on my end.
Maybe it was, I don't know if Renato is out, I think. Well, I think we can continue. Let's see how it works, okay?
Okay. Yeah, please let me know if there's still problems.
Yes, sure, go ahead.
All right. So yeah, I was just introducing the entire Mars family portrait. We have a lot of missions that were sent to Mars from all kinds of countries and institutions, mostly the United States and the Soviet Union in the past, and then Russia, but also Japanese, European missions, and lately also missions from China, India, and the Emirates. Among all these missions, over the last decades, 43% have failed, so it is risky. Although over the last 10 years, we've gotten a lot better at doing this, and over the last 10 years, we've had about a 90% success rate. So we're getting better at it. And there's a lot of late interest, but let me tell you some milestones here. The first actual close-up pictures of Mars were taken by the NASA spacecraft called Mariner 4. I think that's up here. That was in 1965. A few years later, Mariner 9 was actually the first spacecraft to enter Martian orbit in 1971-72. And the same year, also in 1971, the Mars 3 mission by the Soviet Union was a successful orbiter with a lander that performed the first soft, successful landing on Mars. Unfortunately, the lander failed after a few seconds only, so we don't have pretty much any data from the surface from 1971. But a few years after, the NASA Viking missions were extremely successful. They had orbiters and 2 landers, and those landers were very successful. We got years of scientific data from the Martian surface from Viking 1 and 2, and we're still working with that data now. The 80s were a little bit of a gap. There was not much in terms of Mars research going on in the 80s, and it kind of restarted in the mid-90s with the next NASA spacecraft, and actually also the very first rover on the surface. Mars Pathfinder included the little rover Sojourner here, which was our first surface rover. After that, a few years later, it followed up. Some people may remember Spirit and Opportunity. Those 2 solar-powered rovers, they worked very long. I think Opportunity lasted for 14 years on the Martian surface. And a few years later, we had another lander called Phoenix, followed by a similar lander more recently InSight, and then also the bigger Curiosity rover starting in 2012. And the mission I'm talking about today, Perseverance, or Mars 2020, is basically the sister rover from Curiosity. It looks very similar. It has a similar general design, but it has a different set of instruments on board. Okay, here we go. So why do we actually send missions to Mars? The defining question for Mars exploration was always, is there or has there ever been life on Mars? And anytime we talk about life, we need to talk about water. And therefore, we need to look for water on Mars. And that's why previous NASA missions always were designed under this follow the water theme. And once we know where the water is and was in the past on Mars, we could follow up with the next theme, which was more explore the habitability. Follow the water were missions like Opportunity, Spirit, follow the habitability. So looking for potential past habitable environments was, for example, Curiosity rover. And now the next step in this process is seeking actual past or even present, if possible, signs of life on Mars. And part of this, the first active rover, part of this is the 2020 rover, Mars 2020, also known as Perseverance. This is a little outdated. The Exomars rover by ESA was delayed, so this will likely fly in 2022. So let's take a look at Martian topography. This is a map of Mars, a topographic map. Shown here are all the landing sites of past missions and also current missions like Jezero crater, which is the landing site of Perseverance, Mars 2020. Also in red here is the potential future landing site of the Exomars rover by the European Space Agency. We can see two things here. First of all, you can tell that there's quite a dichotomy between the southern hemisphere and the northern hemisphere on Mars. You can see the northern hemisphere is much flatter and lower in elevation than the southern hemisphere, where you have much higher elevation regions, much more mountainous. Valles Marineris is here, famous valley. And you can also see that nearly all of the previous missions have kind of landed in this equatorial latitude. We had Viking, which landed in mid-latitude range, but only one mission so far, which was Phoenix, landed in the polar region. And that's because that was a mission that was only supposed to be short-term, because the problem with landing anywhere close to the poles is the extreme pressure changes during the winter, for example, and the available, even more so, the available solar energy. So Phoenix only lasted till winter started. At that point, it was not expected to survive, and it did not. And also a lot of past missions, especially, were solar energy powered. So if you're going closer to poles, you're losing nearly all or most of your energy the closer you get to a polar winter. And so that's the reason why we see most of the missions, and we'll likely see most of the future missions in this kind of equatorial, maybe mid-latitude range. The latest rovers, both Curiosity and Perseverance, have gotten a little more independent of solar energy. And they still need to heat up and things like that, but they have, instead of solar arrays, they work with radioisotope batteries, meaning they're nuclear powered. So, as you've probably seen in the news, Perseverance landed very successfully on February 18th this year. And for some context, I have said before, we are following the water, and Perseverance is no different. We are still following all these missions, following the water on Mars. And now there's plenty of evidence that water flowed on Mars in the past. Mars today, on the surface at least, does not have the typical characteristics that we think of a habitable environment to have. It is much too cold, it is much too dry, and it suffers quite intense bombardment by solar energetic radiation. Mars does not have this magnetic field that we know from Earth that protects us here. And so there's no known Earth life that we know of that could survive under these Martian conditions. For example, even at the Martian equator, temperatures drop pretty much every day down to negative 70 degrees Celsius. But on Mars, it wasn't always this way. It is pretty much confirmed nowadays in the scientific community that Mars used to have liquid water running on the surface in the past, when the conditions were much warmer and much wetter, and Mars had a denser atmosphere. Therefore, we believe Mars had all the basic building blocks that are necessary for life. And if there was ever life on Mars, we would expect that maybe some signs are still there on the Martian surface of past life that we can find today with these missions. Now, here's a closer look at the Perseverance landing site. This is Jezero crater. It's an ancient river delta. So you can nicely see here the outflow into this crater of an ancient river, and here you see that delta formation with some impact craters. And Jezero is special in that it has rocks and minerals that could only have formed in a liquid water environment. And some of those are commonly associated with life on Earth. And this is why Jezero is such a great place to look for signs of past habitability and even past life. If we look at river deltas on Earth, here's an example from Alaska, just to picture this. These are very, very habitable places on Earth. There are others like the Nile running through the Sahara, or even the Amazon River has a very, very habitable, teeming with life river delta. And so we want to answer this question, did Mars ever have life? And that's what the mission goals want to answer. So Mars 2020 will look for signs of past life itself and also prepare for future human exploration. And so here's a little overview of the mission goals set by NASA. 3 of the goals are about the search for ancient microbial life here on the left. And 1 additional goal is about preparing for future human exploration. So the main goals for the microbial life can be summarized as geology, astrobiology, sample caching, and the future human exploration goal is to prepare for human exploration. And I'll talk a little bit more about each of these goals. So let's talk about geology. The actual goal is to carry out an integrated set of context, contact, and spatially coordinated measurements to characterize the geology of the landing site. And first of all, before you actually fly, you have to pick a landing site. And no matter which landing site is picked, all these options are studied in great detail from orbit, from our Martian orbital assets, from Martian satellites. And this is how we learn what places are great places and a mission to study in more detail. So on the far left here, we go to the largest scale. These are satellite images. You investigate potential landing sites like Jezero crater and the river delta there. And once you send a mission, you can investigate the geology more closely from the local neighborhood and on the meter scale down all the way to microscopic level. And all this knowledge of the geology will reveal the history and the origins of the area. Now, the second big goal is summarized as astrobiology. So we want to find and characterize any ancient habitable environments. Astrobiology always links to habitability. And so for this, we will identify rocks with the highest chance of preserving signs of ancient Martian life, if it was ever present. And within those environments, we then seek those signs of the life. So here, this image is an example of, this is curiosity, not perseverance. But it's an ancient mudstone on Mars, which only forms in ancient lake beds. So in very watery environments that we from Earth know always contains life. So we want to study the rocks and soils in that area to look for these telltale fingerprints of potential ancient life. The third big goal of the mission is to collect samples. And this will be the first mission that actually prepares for a sample return. One of the big goals is to take rigorously documented samples on the Martian surface, put them in sample caches, and in a future mission, return them to Earth. Because one thing we have to understand is while the instruments on these rovers, on Perseverance, for example, are extraordinarily well designed, they're always very limited by their mass and their energy consumption. So we will likely always have the most powerful labs to us available to study these things here on Earth. So that's why one of the goals of the mission is to collect these samples, store them in sample tubes that a later mission then can retrieve back to Earth to study here in more detail. And the final goal is to prepare for human exploration. And this is kind of threefold. First, we want to demonstrate technology that future human explorers might be able to use. So for example, one of the instruments on board is an instrument that's making oxygen from the Martian atmosphere. by chemical reactions. The second big objective here is to characterize the atmospheric dust, right? Mars is a very, very dusty place. And we need to understand the shape and size of these dust grains to understand how they may affect surface operations or assets on the surface, be it mechanical or human health. Even though you might be protected inside the spacesuit, Apollo missions to the moon have shown us that even going back into your habitable area, you will always carry the dust with you. And we need to understand how dangerous this microscopic dust is for human exploration. And the third main objective as part of this goal is to actually measure the surface weather, mostly to validate our existing global atmospheric models of Mars. So to achieve all these goals, Perseverance contains 7 main instruments or instrument groups, which you can see here. Those instruments, WIMFAX, MASCAM, MOXIE, Supercam, MEDA, Sherlock, and Pixel, they are developed in the United States, Spain, and Norway. MEDA is a Spanish instrument developed in Spain, and WIMFAX is a Norwegian instrument. When I say, for example, developed in Spain, that still means there are a lot of international contributions going into each instrument. For example, let's take MEDA, the weather station, contains a humidity sensor that was developed in Finland. And MEDA is then put together in Spain and sent to NASA in the United States to be put on the rover. Now, NASA is very interested in these international contributions for 2 reasons primarily. It alleviates NASA funding. NASA saves money by having other institutions, other countries build their own instruments on their rover. And additionally, it helps reinforce collaborations, international collaborations with NASA's international partners. So let's take a quick look at each of these instruments. The first one is MASCAM-Z. You can see here MASCAM-Z is on the rover mast, on the, you can call it the head of the rover. It's these 2 cameras here. MASCAM-Z will be the main eyes of the Mars rover. It will pick out the best rocks to study. Its cameras have a zoom function, can focus very clearly on distant and close targets, can take 3D images and high-speed video to allow for really detailed examination of even distant objects. And MASCAM-Z will help geologists choose specific targets that we can then drive the rover to and investigate closely with other instruments. Color-wise, it has a color quality, so the quality is similar to a digital consumer camera. It takes pictures with an image size of 1600 by 1200 pixels and has a resolution of about 150 micrometers. Now, the next big one, also on top of the rover on the mast, is Supercam, which looks like the eye in the head of the rover, if you want to call it that. Supercam is a combination of a camera, a laser, and a spectrometer. And it's there to seek organic compounds that could be related to past life on Mars. And what it does is it basically it shoots a laser at surfaces up to 7 meters away. It basically zaps these rocks, and by evaporating materials from that surface, the spectrometer, as part of the camera, can identify the chemical and mineral makeup of these targets. And these can be targets as small as a pencil, as the point is a pencil, from a distance of more than 7 meters. The next instrument is Pixel, or the Planetary Instrument for X-ray Lithochemistry. It's an X-ray fluorescence spectrometer, basically, and it can also identify chemical elements at a tiny, tiny scale, more close-up to the rover. It additionally has a camera that takes super close-up pictures, like a little microscope, of rocks, on the texture of these rocks and the soil textures. And it can easily resolve something that's smaller than a grain of salt, for example. And together, these instruments help scientists to look for these signs of past microbial life on Mars. Excuse me. Another very exciting instrument is Sherlock, which stands for the Scanning Habitable Environment with Raman and Luminescence for Organics and Chemicals. Great abbreviation. This will be the first Raman spectrometer, the first UV Raman spectrometer to fly to the surface of Mars. It is not on the mast, but it is mounted on the robotic arm of the rover, so it can get very close to samples in the surroundings of the rover. And it uses spectrometers, again, a laser and the camera, to search for these organics and minerals that may have in the past been altered by a watery environment and may still contain these signs of past microbial life if you find them. An interesting fact is also Sherlock is the first instrument that will carry a Martian meteorite back to home, to Mars. Basically, there are meteorites that are originating from Mars that have come down on Earth, that we found on Earth, and Sherlock, as part of its calibration target on board, carries a little slice of one of these Martian meteorites back to Mars. It's a fun little effect there. Part of Sherlock is Watson, which is the wide-angle topographic sensor. This is basically a context camera for Sherlock. So it's it assists Sherlock as a color camera for taking these close-up images of the rock grains and the surface textures to basically get a visual image of what Sherlock is measuring with its Raman spectrometer. And these instruments together will help us look for these biosignatures. Basically, any objects, substances, or even patterns that can only be created by life-based processes, like patterns in the rock, or even specific isotopes of certain chemicals that on Earth we know only life could have left behind. So to say, a fingerprint of life. Another instrument on the rover is built in Norway is RIMFAX. RIMFAX is basically a ground-penetrating radar. It can see, it's the first in-situ radar to fly on these rovers, and it can use the radar to detect underground structures, like ice underground, rock, or sand, or even liquid water potentially, like subsurface ponds or lakes. Similar to previous rovers, like Curiosity, for example, Perseverance has also its own weather station. This is known as MEDA, or the Mars Environmental Dynamics Analyzer. And as part of MEDA, there are 6 different instruments or sensors to measure wind speed, wind direction, pressure, relative humidity, air temperature, ground temperature, radiation in UV, visible, and infrared. And MEDA fulfills 2 of these future human exploration objectives of NASA. It's one thing to assess the effect of airborne dust on the operations of these surface systems that I talked about earlier, and also on human health for potential future astronaut exploration by analyzing the size and the morphology of these dust grains in the Martian atmosphere. And second, it helps us improve the predictability of forecasting models simulating the Martian climate and the Martian weather conditions. And to do that, it measures all these variables around the clock. Another interesting instrument on board is MOXIE. MOXIE is a technology demonstrator. And this is the instrument that I kind of alluded to earlier, that is able to create oxygen as a test demonstrator here in this case, from the Martian carbon dioxide atmosphere. Carbon dioxide is about more than 96% of the Martian atmosphere, whereas oxygen is only 0.13% compared to Earth's 21%. And so what MOXIE does is it collects the CO2 with a compressor from the Martian atmosphere, and then electrochemically splits the CO2 molecules into carbon monoxide and oxygen. And this is to demonstrate our capability for the future to potentially use this to create oxygen to breathe, but also oxygen as an oxidizer for propellant. Another core of the mission, as I mentioned earlier, is the sample retrieval. And so in the belly of the rover, you have this entire sample retrieval system. Perseverance will be the first mission who will collect 35 samples of Martian rock and regolith, each about 15 grams, that will be drilled from the surface into these sterile sample tubes. And then these tubes will be dropped at location to be later on collected by a sample return mission. The tubes are about the size of a small cigar, 13 millimeters diameter and 60 millimeters long. And the strategy will look like this. From the landing site, the rover will drive to regions of interest that we identify as regions of interest for habitability or in potential life, drill these core samples there, put them in these sample tubes, and then dump them all in one or two collection sites. So the rover will move on to different areas of interest and then bring these tubes back to the collection site, so that a future mission then that will pick these up only has to go to one place to pick up these caching tubes. And so in a sense, Mars 2020 Perseverance is only one part of a three-part Mars sample return campaign. We are here with the rover collecting these samples and dropping them in specific locations. In the future, and we are hoping within the next decade or so, there will be a follow-on lander that contains an ascent vehicle and also another little rover that is just there to pick up these sample tubes and to bring them back to this ascent vehicle. The Mars ascent vehicle will be built by NASA, and it will deliver these samples back into Mars orbit, where an ESA-developed Mars orbiter will rendezvous with the ascent vehicle, capture the samples, and then bring them back to Earth. So this is a big mission campaign attempted by NASA and ESA together, hopefully in the next decade. Additionally, as another technology demonstrator that you might have heard more about is Ingenuity. Ingenuity is a little helicopter, like a drone, mounted under the belly of the rover, which safely brought it to the Martian surface, and it will be the first helicopter attempting to fly on another planet. This is only a flight test, so there's no specific scientific instrument on that little helicopter. It's just there to be as a technology demonstrator to show this capability. And flying a helicopter on Mars is quite tough compared to Earth. Mars has a very thin atmosphere. The Martian atmospheric pressure is only about 1% or so of Earth's atmospheric pressure. So therefore, the density is also much less. And therefore, the Ingenuity helicopter has to be very, very light, has to have quite large rotor blades, and the rotor blades have to spin much, much faster than what would be required on Earth. Martian gravity helps a little bit with that, because Martian gravity is only about a third of Earth gravity, but still it's a much tougher requirement for a helicopter to fly on Mars than on Earth. Now, if Ingenuity succeeds in this test, future Mars exploration could really include an aerial dimension. It could include more drones used for reconnaissance to figure out where we want to drive, where there are specific areas of interest for us, for our scientific investigations. And so this is a very, very interesting technology demonstrator that hopefully within the next few weeks or so will have its first test flight on Mars. Now, after I talked about all the instruments, just a quick recap. You've probably all followed this in the news. The rover was launched in July last year. Took about 7 months, launched on Atlas V to get to Mars, which is about 314 million miles. And about 78 miles above the planet, the spacecraft entered the Martian atmosphere. Now, in comparison to previous missions, Perseverance has some really good terrain detail knowledge. What it does is while descending, it takes images of the surface and then compares these to an orbital map we have of that landing area. And based on that knowledge and knowing what are good places to land within that map and what are dangerous places to land, Perseverance was able to steer and divert to locations that are safer for us to land. And to illustrate that, these are the so-called landing ellipses of different Mars missions. This is actually Jezero crater here with the delta, which you can probably see here a little bit. This is the landing ellipse of Mars 2020, about 7 kilometers across. Whereas even the previous sister mission, MSL, had a much larger landing ellipse without that capability, and missions before that even larger than that, like Phoenix here and Mars Pathfinder. And without these new capabilities, we would not have been able to land in certain regions that are more dangerous for landings, be it because there are big boulders or cliff faces. Here, for example, we have these, and if MSL had flown to this area, we would have quite a good chance of landing here somewhere along the edge of the crater, which is dangerous to land in if you land on a slope. So that's the added capability of Mars 2020 in the landing smarts category. Now, you might have seen the coverage. It took only 7 minutes from entering the atmosphere to reach the ground. I can tell you it felt very, very fast. On the way down, the capsule steered its way through the Martian atmosphere. The heat shield slowed it down from 13,000 to 900 miles per hour. And I'm very sorry for all the imperial miles per hour and such units here. It took me a while to get used to them as well. Then Perseverance used a new parachute. This is an actual picture of the parachute opening here, looking up at the parachute. That further slowed down the spacecraft to about 180 miles an hour. At that time, it also dropped its heat shield, which was no longer needed. Now, this is looking down at the heat shield just a second after it was dropped. And then one of the final stages is the descent stage using its retro engines to fly the rover down to the last mile to the surface, basically. And it's a similar system with the sky crane as Curiosity used in the past, where the descent stage lowers the rover on this crane. And we also have nice images from that video where this is looking up from the rover, looking at the descent stage. You can imagine, this is the descent stage here. These are the 3 cables the rover is suspended on, with the data coming through this cable here. And looking the other way, this is looking from the descent stage onto the rover. This is just basically less than a meter above the surface, just when landing. And by this point, it was slowed down to only 2 miles an hour so that we can assure a soft landing. For communications, Perseverance communicates with the NASA Deep Space Network, which is in 3 locations around the globe, in California, in Spain, and in Australia. And while some communication goes directly from the rover to these antennas on Earth, most scientific data comes actually down via relay. So the rover uses satellites in Martian orbit like ESA's Trace Gas Orbiter or Mars Reconnaissance Orbiter by NASA to relay any data, any scientific information from the surface via the satellites to the Deep Space Network on Earth. And this communication window takes some time, which you might have noticed if you followed the coverage during landing, that we will never have live coverage because it takes, depending on location of Mars and Earth, between 5 and 20 minutes for any signal to travel between Earth and Mars, just by the speed of light. Now for power, Perseverance carried a large battery, charged by a nuclear generator. It's called the Multi-Mission Radioisotope Thermoelectric Generator, provided by the US Department of Energy to NASA because it's nuclear. And it's not a nuclear reactor in a sense, as you imagine reactors on Earth. It's a radionuclear generator that uses just the natural radioactive decay of plutonium dioxide to create heat, and then using what's called the Seeberg effect to create power from that heat. And all in all, that nuclear generator produces only about a constant stream of 110 watts of electricity, and that's at the beginning of the mission. It decays over time, so towards the end of the mission, this will reduce further. So this is a little more than a strong light bulb. So you can imagine that with 110 watts, it's going to be tough to power all these instruments on the rover. And that's why we need big batteries on the rover, and that's also why we cannot power all these instruments 24 hours a day. So that explains why the rover needs to sleep quite often on the surface to regenerate some of its battery power. The prime mission for this rover is 1 Martian year, which is about 2 Earth years. And we've learned a lot from previous missions, especially Curiosity, which is a very similar rover, in that we believe we can achieve a lot more in shorter time nowadays. We can drive further on average in a day, which allows us to get to more remote destinations than previous missions. And so to wrap up this summary here, the 2020 Mars Perseverance mission will tell us about the history and the origins of Mars. It will provide information on promising locations most likely to have harbored water in the past, and therefore being habitable and potentially harboring past life. And it will also pave the way for future human missions to Mars. So now let me talk a little bit about my personal involvement with the mission. I'm a participating scientist with the MEDA team. So if you remember, one of the instruments on the mission was the Mars Environmental Dynamics Analyzer, the weather station. And I'm part of that science team on that instrument. And this means I focus on analyzing data returned from this instrument. MEDA contains all these different sensors, which includes air temperature sensors on multiple locations on the rover, the humidity sensor on the mast, the thermal and infrared sensor, looking down at the surface and looking up at the sky, 2 wind sensors on these booms on the mast, and a radiation and dust sensor on the top of the body of the rover, and a pressure sensor inside the body. And additionally to analyzing all this data from these instruments, I'm also involved in day-to-day mission operations, which means I help plan mostly atmospheric activities, like, for example, atmospheric opacity measurements, dust size measurements, observing dust levels on Mars, and day-to-day weather station activities. And all that for tactical planning, which usually means planning what the rover does on the next day, and also more campaign planning, which is longer term planning. And so as part of this MEDA instrument, before the rover flew, I've been involved in humidity sensor calibration. So the humidity sensor, as I've shown, is one part of the MEDA instrument. And here in these plots, you can see the typical Martian ground temperature and relative humidity curve throughout the 24 hours of the day. This example here is for the previous Phoenix mission, but it's not too different from other locations on Mars. And we can see during daytime here in the middle of the day, Mars can get relatively warm, up to 260, or depending on location, even 280, 290 Kelvin, which is comfortable even on Earth. So, but at that time, obviously besides the low pressure, it is also extremely dry. The relative humidity is near 0 at this time, whereas in the other extreme at night, the Martian temperature can drop all the way down to 80 and lower Kelvin, which is extremely cold and extremely tough for any kind of instruments you have on the rover. But at the same time, this is for me a very interesting time because the relative humidity at that time can get very high. Relative humidity can even reach saturation levels on Mars, which is very interesting, for example, for things like frost formation. When you get relative humidity above 100%, you have frost, for example, forming on the surface. And we've seen water frost with the Viking missions and with the Phoenix lander as well. And so what we've done here at Michigan is, in the past, we've developed our Michigan Mars Environmental Chamber, where we can simulate this entire range of Martian pressure, temperature, and relative humidity conditions. And we can use this for scientific investigations or for calibrations of instruments like the humidity sensor on board Perseverance. And this is just me here with the Finnish humidity sensor team. So I alluded to that before a little bit. While MEDA is a Spanish instrument, some sensors of it come from all over. And so the humidity sensor specifically, also the pressure sensor, were developed by the Finnish Meteorological Institute in Helsinki, Finland. And they came here with their instruments to calibrate the humidity sensor. So now, why am I even interested so much in mainly temperature and relative humidity, especially? I'm interested in any surface atmosphere water exchange mechanisms. And this can be on a longer time scale, like if you're saying interannual, year to year, or especially also on a diurnal time scale. And there are multiple mechanisms that the surface can exchange water with the atmosphere. Those are mainly physisorption, which is physical adsorption on the surface of water molecules, salt hydration, which is salts that exist in the Martian regolith, in the Martian soil. They can hydrate, meaning they change the hydration state, meaning inside the salt's crystalline structure, they incorporate water molecules. This does not mean that the salt turns into a liquid water solution. That would be brine formation. Brine formation can happen when salts in the surface, for example, absorb water vapor and moisture from the atmosphere and therefore turn into a liquid solution. This process is called deliquescence, and the opposite is efflorescence. And the fourth mechanism for surface-atmosphere water exchange that's also very interesting is frost formation, which happens when the relative humidity gets very high, mostly during the night or early morning hours, to be expected at that time. And I specifically focus on the middle two here, on salt hydration and brine formation. And now we'll go a little bit more into detail. Salt hydration on Mars is a very interesting topic. On the left figure here, we see a temperature plot versus the relative humidity on Mars, and this is for magnesium sulfate, which is one of these very interesting salts on Mars, because within the Martian range of conditions, which is kind of highlighted here with that entire gray strip area here, we pass through multiple stable salt hydrate, or in this case, magnesium sulfate hydrate regions. So we expect that different hydrates of magnesium sulfate are stable on Mars at different times of the Martian day. So that means that we might see a change in hydration state of these salts throughout the Martian day, and therefore these salts absorbing or releasing water vapor from the atmosphere. This is the example of magnesium sulfate. This plot here is just rotated its temperature and pressure and water vapor pressure. And again, we see the diurnal variation here of conditions on Mars. And we see that for the calcium sulfate example, between, also known as basanite and anhydrite, we change between different hydration states of this, in this case, calcium salt. And so that's interesting for salt hydration because we cover all these conditions on the Martian surface. On the other hand, brine formation, and this is quite a complicated figure here, so stick with me. The Martian relative humidity range, you saw it earlier, can go up to 100%. At night, temperature range can also go between 180 and 260. And within that range, we have these dotted lines here, which are these deliquescence lines. So if we start from the right here, from low relative humidity, and go left at a specific temperature, a crystalline salt in the surface will at some point pass this line, which is called the deliquescence line, which is where the salt solution will be stable. So the salt at this point absorbs water vapor from the atmosphere and goes into solution, creating a liquid water, a very salty liquid water, a brine, on the Martian surface. And this has been detected only so far at Phoenix, very temporarily, so in the polar region. And we can see here in all these dotted points are atmosphere and ground data points of previous missions. But Phoenix, for example, if you look at Phoenix temperatures at the ground, passed through this kind of triangle here, so through these stable liquid phases of brine on the Martian surface. And similarly in the subsurface, these might even expand even more. And so we would expect under certain conditions and temporarily within the Martian day that we may be able to see these salts deliquescing and forming a liquid brine, liquid water on the Martian surface. And this very salty liquid brine is much more stable on Mars than pure water. Pure water would very quickly evaporate. And again, why we're interested in this? Because liquid water is one of the key things that we need for life to exist on Mars. One tool that we can use on the Mars rover is SHERLOC, which is Raman Spectroscopy. So SHERLOC is the Perseverance Raman spectrometer. And we know that, for example, to observe salt hydration, if we look at the Raman spectrum, for example, in the sulfate range here and in the OH range, we see changes in these peak positions based on changes in the salt hydration state. If we're going from, for example, epsomite to hexahydrite all the way to kieserite and lower hydration states. We see these shifts in the Raman spectrum, and this could allow us to detect these hydration state changes in the salt using Raman spectroscopy. Similarly for brine formation. We've done experiments in our lab, for example, where we exposed salts to water vapor in the atmosphere, for example, and use that deliquescence. We follow the diurnal cycle on Mars in temperature and relative humidity, and we potentially see deliquescence happening under Martian conditions. And again, Raman spectroscopy can be used to find this on Mars, because the Raman spectrum between a crystalline salt that is just hydrated, for example, calcium perchlorate, and a liquid brine, so a liquid solution of the salt, the Raman spectra look very different. So we're hoping that we can use the Sherlock Raman spectrometer to investigate this potential salt hydration and brine formation along Perseverance's traverse. And we're looking into campaigns utilizing both a combination of MEDA for the environmental conditions and Sherlock for a Raman spectroscopy aspect to look for these phenomena on Mars. So this was a little bit of an insight of my interest into the mission, and earlier an overview of the mission. And I hope you gained some interesting knowledge from this. And please follow Perseverance as we keep exploring Mars. The rover itself is very active on Twitter and Facebook, and you can also follow it on the NASA websites. So now, please, any questions you have, I'm open to answer them. I see there was some chat messages already. So let me know if you have any questions. Thank you very much.
All right, thank you very much, Eric. It's a very interesting talk. So I guess I'm gonna open here for the attendees questions first.
Marcel is joining.
Okay.
Marcel has a question.
I don't see Marcel. Oh, there he goes.
Yes, can you hear me?
Yeah.
Okay. Hi, Eric. Thank you very much for this very nice talk. It was very, very interesting. And I have two general, maybe naive questions. You show all the steps concerning all the steps that are necessary for the human presence soon on Mars. Okay. But my question is the following: is maybe the most challenging task is the 6-month travel to Mars?
Yes, I agree with you there. The 6 months travel is one thing, that's true, but also we can't just go there, do some investigation and come back immediately because of the orbital constellations. So I believe if we go there with the intention of coming back, we need to wait at least 2 years to have a good window again, or close to 2 years to come back. So yes, that is a big challenge, especially when it comes to the radiation environment, right? You have the solar radiation in space while you travel to Mars, those 6 months that you mentioned. But also, as I mentioned before, Mars does not have a magnetosphere, really, not a strong magnetic shield that protects us on the Martian surface from this hazardous solar radiation. And so you bring up a very good point. That is a very big technological hurdle to overcome. And there have been multiple suggestions for the future, like if we go to Mars with human exploration, do we try to build a habitat underground, for example, that can kind of shield us from the radiation? If not, then any surface structures that the astronauts would live in would have to be very well shielded, which of course is again a big problem with weight, because any kilo you bring additionally on a mission like this brings a lot of more kilos that you need in propellant to bring it into orbit, etc. So yeah, I think this is a big question, an important question, and a question that is not yet completely solved.
Okay. And my last question is the following, concerning the astrobiology and also all the experiments linked to astrobiology, how is the procedure of sterilization for avoiding the contamination of the Mars environment by life taken from Earth to Mars on the rovers?
So that's a very good question, because when it comes to this whole field is often summarized as planetary protection here by NASA. And it's twofold. As you're saying, you want to protect Mars from being contaminated by spores or like microbes from Earth, because A, you don't want them to multiply there, and B, if you detect life there, you want to make sure that it's life on Mars and not life that you brought.
Yeah.
And so any surface asset that flies to Mars currently is very well cleaned in during the building phase and before transport to the launch vehicle. Even in the launch vehicle, it is cleaned very well. Not every instrument nowadays is baked anymore. Viking, for example, was quite baked, but as far as I know, and this is a little bit outside of my field, but as far as I know, this is not being done anymore. Still, there are constant tests on any instrument and spacecraft surfaces during the construction and before launch to make sure that there's a very low limit contained to microbes per square meter, basically. And on the other side of it, you also want to make sure that what you bring back from Mars is safe to bring back on Earth. I mean, who knows what we might find there, basically. And that whole aspect is covered by really carefully sealing these sample tubes on a Perseverance mission, for example, because it is hard to seal something really well that nothing gets in or out, but it is a whole other matter that these will have to sit on the Martian surface for at least 10 years, I assume, to then be picked up and brought back. And so, but yeah, back to that first thing of cleaning. Another thing that's currently being done is we currently do not land on Mars in the most likely regions to currently contain water. There are some Martian regions where the likelihood is higher to temporarily contain liquid water that we are not landing in, because we currently do not want to go to these regions, accidentally bring microbes, and then have them multiply in that region there. And so that's why, for example, Jezero crater, from a water perspective, from a current water perspective, might not be the most interesting place. It is a very interesting place for past water, to investigate where past life might have existed. But there are some papers, especially in the recent years, where they have discovered some potential subsurface lakes, things like that. Those are places where the current missions, at least, are not going, because those are exclusion areas for planetary protection purposes.
Okay, thank you very much, Eric.
You're welcome.
Okay. So, we have some questions from the YouTube. Flavia Rommel was asking for you to speak a little more about the oxygen experiment on board, the process of how it's working and selecting oxygen, perhaps storing it. And also if the colors and patterns of the parachute had some specific meaning.
Yes, so let me start with the second part there. They had a hidden meaning, that is true. I don't quite remember the exact wording, but I think what was encoded was the motto, I think the NASA motto, or I think it was the JPL, the Jet Propulsion Laboratory motto, and I think the coordinates in latitude and longitude of the Jet Propulsion Laboratory, JPL, in California. And I think those two things were encoded in that parachute pattern. The latitude and longitude of JPL, and I think their motto. Yeah. And then
the Martians would know.
Yeah, I don't think the Martians know. I think this is more of a public outreach thing by NASA to get people involved in seeing that pattern and being interested in trying to solve it. I think it took only, a day between the video being made public of the parachute landing and the first people figuring out the coded message. Yeah, and to answer the other question, I can try to do my best. I don't know every detail about the engineering of MOXIE, but to keep in mind here is MOXIE is a technology demonstrator, so it is not meant as of now to really store oxygen for future use. Perseverance as a purely robotic mission does not really need oxygen for anything. It is there to demonstrate future capabilities of future instruments that will be bigger. What MOXIE does is it uses a compressor to accumulate Martian atmosphere, which is mainly CO2, to compress it into a pressure where it's much easier and much better to create oxygen and higher amounts of oxygen than at Martian pressure, which is very low. And then it uses an electrochemical process to split the CO2 into a carbon monoxide molecule and oxygen molecule. And that can then be separated, and we can show in MOXIE can detect whether we successfully created oxygen. And I think on the current rover, this will then just be released, this created oxygen, because it has no use on a robotic mission. Because this is just to demonstrate that we have the capability for future missions. And I assume future manned missions will then have a much bigger version of this MOXIE instrument or something similar that will actually produce usable amounts of oxygen for human consumption, for breathing, and also potentially as propellant. And if you're then talking about propellant, like for return vehicles, that includes a lot more infrastructure, because then you have to pressurize this propellant, purify it, pressurize it into a liquid form, because typically oxygen propellant is most likely liquid oxygen. And so there are a lot more steps until until we get useful amounts of oxygen for future missions. So MOXIE is just the first little step in that process.
Okay. We have another question. Let me just ask you one thing first, which is it was not very clear to me about the sample storage for later retrieval. So does that mean that the next mission would be already limited by the location where it's going to land? And alternatively, why isn't it cheaper, or better to send a small rocket that goes with this mission and just goes back to Earth afterwards?
That's a very good question for NASA headquarters. But first of all, yes, this will restrict this sample return mission to land close enough to these dump sites where we store the samples on the Martian surface, such that a small rover can actually go to the actual location and retrieve them. Yes, so we will need to land again in close proximity. I'm speculating a little bit now here. So this is partially personal opinion. I believe the future mission that will collect these will be less of a science-heavy mission in terms of lots of science instruments, where it would be more interesting to go to a new place, but more of a purely engineering mission of a little rover that picks these up, brings these to an ascent vehicle, and then the whole complex engineering of this ascent vehicle, the orbital capture, and the return. Now, why has this not been done at once, basically, where we collect the sample and then immediately return it? I personally believe because the technology is not as mature yet. Basically, if NASA had wanted that capability on this mission, the mission would have gotten much bigger in scope, would not have happened right now, would have taken at least another decade. And I think that's part of the reason why this approach was chosen with these multi-mission campaign.
Okay, thank you. So I have two questions from Andrea Galarza. The first one is, does all the instruments on board Perseverance they are available at any time, or its use is prioritized depending on the scientific goals?
Yes, that is a very, very good question. Typically, there are some instruments who may interfere with each other. So just for example, the radar might not be running when we're trying to send data to orbiters or things like that. Or for example, you have multiple instruments on the robotic arm. You have Watson, Sherlock, and other instruments on the robotic arm. So depending on what we plan to do, we can only use one of these at one time. But there are other instruments that don't interfere with those. For example, MEDA is a great example. we can quite often do MEDA measurements, weather measurements basically, while we are doing other observations. MEDA is quite independent in that sense. We can obtain the atmospheric temperature and the surface pressure and the ground temperature, for example, while we are looking at one target with another instrument. So that depends a lot on the instrument. Additionally, currently we're still very early on in the mission. So we're just, finishing up, testing out all the instruments, calibrating things. So at the beginning, it is often very conservative, where we say, okay, we use one instrument at once, figure it out, make sure it works, and may not interfere with anything else. And once we're done with this instrument, we do this other instrument. So that also limits the number of instruments we currently use at the same time. There are more factors, for example, power. Some instruments, for example, MOXIE, again, the oxygen generation, uses up a lot of power to do this electrochemical process of splitting the carbon dioxide into carbon monoxide and oxygen. Requires so much battery power that when MOXIE is running, which will be quite sparse in this technology demonstrator, we will likely not be running many other instruments on that same day. The additional consideration also related to power is that the rover cannot, as I said earlier, the rover cannot run all the instruments all day long throughout the Martian day and night, because the rover needs to conserve power. At night, it needs to heat itself to keep the instruments alive. That requires power. And so there are times where the rover just goes to sleep, regenerating its battery power, basically. And that's also a limit on the availability of scientific data and instruments.
Mm-hmm. Okay. And the second question, maybe it's related to the first one. What's the strategy regarding sending signals from Mars to Earth? When to send signal and when to hold them on? I'm assuming that, for example, at night, you will not be sending.
Well, that's an interesting question as well. So we are very much confined by two aspects. For one thing, if we want to send direct signals from the landing site, from the rover to Earth, they are usually called direct from Earth or direct to Earth, depending on the way to go. These signals can only happen, of course, when the site that the rover is on Mars is facing Earth. So if we are in the shadow of Mars, we cannot send direct signals. For operations reasons, these are often done once a day, and the direct signals to Earth often contain the engineering data, the important survival engineering data. Whereas scientific data, as I mentioned earlier, gets most often sent via the relays in orbit. And those relay satellites also allow us to send data at other times of the day when the rover's basically on the away side from Earth, on Mars, and things like that. So then the transmission strategy relies on the orbiting satellite's position. So there are typical times within the Martian day where we have, let's say, MRO, the Mars Reconnaissance Orbiter, flying overhead. And this time of, let's say, 12 minutes of overflight, that the rover can directly see the satellite passing overhead in the sky. That's transmission time for the rover to send science data to MRO. And MRO or any other of these satellites, they can temporarily store that data in their relay function and then transmit it to Earth, because they have much better communications equipment, can send much higher data rates, and have a much longer or much more often see Earth directly, basically can communicate directly with Earth.
Mm-hmm. Okay.
And this happens also during the night. So there are overflights at night as well, and the rover typically wakes up for those. Okay. So if we're in a sleep cycle where the rover is sleeping, conserving energy, if there is an overpass that we use for communications, the rover wakes up for that, for communications.
Okay. Mm-hmm. So there's another one. I had one first that I was curious about, because I remember a talk from Newton some time ago. You were talking about the brines, and I remember, if I'm not mistaken, the brines were interesting in the sense that they could stay liquid for even under very low temperatures, so that you could apparently they could serve as an insulating pocket where, for example, life could be there despite the extreme temperatures on Mars. And if this is true, how deep, probably you don't expect to find them on the surface. How deep would have to go below the soil to find it?
So when it comes to that, that's a tough question. So because we don't know that much yet about the subsurface of Mars, right? We had some, like the Phoenix lander had a shovel on it that dug a little bit, but here we're talking digging about 10 centimeters or something. So anything else we would require radar or drills or things like that. Now, what's interesting though is Phoenix, when digging those trenches, actually discovered frozen brine, definitely, where we could see that was clearly a mixture of very soft ice, like a slush, where basically there was clearly water ice in mix with salt that temporarily, within that diurnal cycle, within a day, it was liquid. And also on the Phoenix lander, for example, on the landing struts, literally the legs of the lander, we saw this the surface salts that were splashed up onto it temporarily deliquesce at very low temperatures and basically forming a liquid solution temporarily. And as you rightly said, that's what these salts can do on Mars, is keep water liquid at a very low temperature. It's kind of, I guess you don't have it much in Brazil, but here I can give a good Michigan example. Whereas in winter, when there's snow everywhere, there's ice on the roads, what you do is you put salt on the roads, right? To melt the ice, even at temperatures below freezing. And that's a similar concept. And there are some salts, while outside here we likely only use sodium chloride, table salt essentially. There are some other salts, especially those perchlorate salts that I mentioned, that can keep water liquid down to 200 Kelvin, or negative 73 Celsius or 74, under certain temperature and relative humidity conditions. Yeah.
It's amazing. Okay, so one question that we had, let me see here, just a second. Okay. All right, so they said, thanks for the talk. Eric, you mentioned a lot of details about the Martian weather, and what about dust storms? Have Perseverance detected any already, and how dust can affect the performance of the mission?
Yes, so I can talk a little bit from the Perseverance is very young, so there's not that much data we have accumulated yet on Perseverance on the surface of Mars. But I can talk a little bit about our experience with Curiosity, which we assume will be similar with Perseverance. As I said, Mars is a very dusty environment, and there are quite often dust storms on Mars, and those can range from the smallest level to global. So about, I think every 4 years, roughly on average, we get a global dust storm on Mars, where even if you look by a telescope from Earth, you can literally not see surface features anymore on Mars because the air is so dusty. And every 4 years, give or take, we have this global dust storm on Mars that we've seen now multiple times. We don't know quite exactly yet why that happens, but it is impressive because if we take, let's say, the atmospheric opacity as a value to measure this, with a typical atmospheric opacity of the Martian atmosphere of 0.9 or 1, of tau equals 1, we go in that dust storm to a tau of 9 equals 9 or 10. So really, really opaque atmosphere suddenly. So this is global dust storms. We have these phenomena once in a while, but much more common are very more local things, down to the size of a dust devil. So what we observe quite often on Mars and have with Curiosity, and likely we'll also with Perseverance, are these little dust devils. They look like little tiny tornadoes that you can see passing by, often observed accidentally by the rover cameras. You see this little dust devil passing by. And those are also very interesting phenomena. Yeah. And when it comes to dust affecting the rover, then yes, it certainly does. And if you look at, you can probably find them if you search on Google. If you look at pictures of for example, of the Curiosity rover, of the surface of the deck of the rover, but the difference between at the beginning of the mission, and now it's quite severe. These missions accumulate a lot of dust, and it is important to spec out all the actuators, especially like the robotic arm that has to be able to move. It still has to be able to move after 2 years, with that dusty environment. Another problem is there for the solar-reliant missions, like Spirit, Opportunity, the InSight lander. They all rely not on a radioisotope battery, but on solar rays for their power. And solar rays, when they get covered with this very, very fine dust film, they lose their efficiency. And that's often a limiting factor in terms of lifetime for these missions. The really long-lasting Opportunity mission, the Opportunity rover, which lasted, I think, something like 14 years, finally died because of the global dust storm that we had.
Mm-hmm.
Yeah.
All right. Thank you. So I'm sorry for so many. You take me a lot of your time. Was a lot of questions. I think we are. Oh no, there is one more hand here. That's Simone herself.
Yes, I also have a question. So, thank you very, very much for this talk. It was amazing. It's an amazing mission. It's very, very nice. And it's like an adventure. I don't want to use this word adventure because I know all these technical details you have to show.
It is though. I think for everyone involved, it is an adventure as well.
Yes, wonderful. I had a question about the solar energy, but you partially mentioned that if it was possible to use solar energy, but not for the full mission, as I understood, but for some instruments to use solar energy.
Yeah, right? some previous missions relied completely on solar energy. They charged their batteries every day by their solar rays. Most of these smaller missions still do, like even the most recent InSight lander used solar rays for its energy needs. And it's still viable and it works. It just comes with its caveats. You need to understand that the mission is likely time limited because we have this dust settling on the solar rays, making them less effective. But one interesting factor that we've learned with these solar array missions is that actually these little dust devils or winds on Mars, which are dust events, can actually help clean the solar rays. So we had instances where we had dust devils pass by and actually clean the solar rays somewhat, and we can really see the effectiveness of the solar rays peak up again after that. So that's also partially the reason why some of these rovers that were solar powered, like Opportunity, lasted so long. Yeah.
Great. And just a small question more. How maybe this dust storm can affect the retrieval of the material retrieval in the future? How maybe it will be covered by dust?
That's a good question. I think covering by dust, that's a topic I think that's not very well yet understood. The whole Aeolian process. There were a lot of Aeolian investigations by the Curiosity mission. I'm sure there will be more by Perseverance, but how do sand dunes travel on Mars, for example? Will these deposited tubes be eventually covered by dust and not be able to be found anymore? I'm pretty sure the location that Perseverance chooses to store these will be in a prominent location that is not likely to be covered by dust. Mars has very variable terrain. We have big patches that are very dust-free, with bedrock basically, whereas we have other areas where we're in the middle of a dune field. And I would assume we're not depositing those in a dune field. But regarding dust storms, I would assume we will, based on the, we now know that the global dust storm, for example, takes about a 4-year cycle. Every 4 years or so, it seems to reappear. And I would think that we will try to not land in the middle of a dust storm, of a global dust storm like that. Obviously, there's still risk involved with smaller level dust storms that are less predictable.
Okay, thank you. Thank you very much.
Okay. So just to make sure I understood this correctly, so you said that there are places where you have actually liquid water very close to the surface, but you're not sending anything there on purpose for contamination.
I mean, these are often indirect measurements. So the paper I was referring to, for example, is I think Orosei et al. 2019, 2018. They, by orbital measurements, they detected what they believe is a very shallow subsurface lake, I think in the southern hemisphere. Any kind of region where, under current guidelines, as far as I know, any kind of region where we might regularly form liquid water, potentially, in good amounts, is, as far as I know, currently not a target for missions like this. If we have a more expensive mission in the future that is even more well cleaned, that we can assure there's nothing coming with us that will survive on Mars, then those, I'm sure, will be targets again. Because this is kind of, on the one hand side, you obviously don't want to bring something accidentally and then have it duplicate there, multiply there. But on the other hand, these areas that are habitable nowadays are very interesting areas to explore, right? So you kind of have to figure out an approach there. And I think in the future, we'll see more daring concepts, I would think, going to more places that may be currently habitable, like some mission that has a drill that can try to find, or better radar that can try to find these subsurface lakes if they exist. Yeah.
Mm-hmm. Okay. So we have time for one more question.
Mm-hmm.
Yeah, we have one more question. I just posted the question to you.
Oh, okay, yeah. Question answered.
Okay. Instead of activity looking for life, would be possible to set up a long-term experiment with a secure humidity shelter, which could provide ideal circumstances to possible let or see Mars spores to grow. I assume that if there is right now, there'll be some sort of dispersion mechanism. Not exactly okay. Let's see here.
Yeah, that's a tough one.
Okay.
Well, first of all, we do not know of any current life on Mars, and we do not currently we do not expect to find current life. We hope to find potentially past life, but if I understand this question correctly, could we basically improve the Martian conditions locally to have current Martian life replicate, or to improve the habitability locally? I think that's the...
I think I understand now. If it's possible to get, suppose there were spores of some kind in Mars. If it's possible to get a controlled environment that would allow it to grow.
Certainly, I think certainly if we find something in the sample probes and bring it back, we can certainly have a controlled lab environment here and try to figure out what we're looking at. On Mars, I think that's a little tougher, and that's a little further looking into the future that I can speculate easily. I think having these facilities on Mars will be quite a few decades out, I think, where that might be possible to do in situ.
Mm-hmm. Okay. All right. I think we tortured you enough. I'd like to thank you again. It's a fascinating talk, and people can be asking questions the entire day. But,
yeah, thank you very much for having me and for your invitation.
So it was a pleasure.
Pleasure was all mine. Thank you very much.